Welcome, everyone. Happy Friday. Welcome back to chemistry class. We are so close to wrapping up this term. We are in our final chapter, and today we are starting the final topic of the final chapter. We're exploring reaction rates, how fast a reaction can go. We've already seen that we can compare experimental data to determine the order of a reaction according to each reactant. Once we know what the order is, then we can pull out a set of integrated rate laws. So far, we've explored the first order integrated rate law, and we saw that the half-life time was really important, and it applies to a lot of chemical reactions and isotopic decay. Today, we're going to wrap up this conversation and look at zero order and second order integrated rate laws, and then jump into our very final topic, which I think is a lot of fun. So first order rate law, we can integrate this. When we do, we see that the format for this equation matches the equation for a straight line, y equals mx plus b. We can line this up with y equals mx plus b and plot ln of the concentration of our reactant versus time. Now, if we just plotted the concentration of A according to time, we would get a curve, which is just a little bit harder to analyze. But if we plot the ln of that concentration, we get a nice straight line. And this is diagnostic. If we see this type of pattern in our data, we know that we have a first order reaction. Well, what if it's a zero order reaction? Well, then we can go to our integrated rate law for zero orders. We know, and we've seen before, that if the rate of a reaction is not correlated to the concentration of A, if it's independent of A, well, then it's a zero order reaction. The exponent is 0. Concentration of A to the power of 0 gives us 1. So all we're left with is the specific rate constant K. The rate of the reaction doesn't matter whether you double or triple or half that concentration. The rate doesn't change as the concentration of your reactant decreases as the reaction proceeds. Well, we can integrate this rate law. We know that the rate law, if it's zero order, is simply equal to the specific rate constant K. We also know from our very initial discussion on rates that we can measure the rate of a reaction by measuring the change in the concentration of the reactant or the product. And it's simply the change in that concentration per unit time. If it's a reactant, we add that extra negative sign in front so that we have a positive rate. If we integrate these two halves, K and delta A over delta T, we end up with the change in the concentration of A, so the concentration at time T minus the initial concentration, and it's simply equal to negative KT. If I move this initial concentration over to the other side of my equation, I end up with my integrated zero order rate law. This is a nice, rich formula. I can now learn about my reaction as time goes by. I can determine and predict the concentration at a certain moment in time. Or I know how long I need to continue my reaction to get my desired products. And of course, we can align this with the equation for a straight line. Y aligns with the concentration of A at time t. And we can plot that on the y-axis. If we do an experiment, we can monitor that concentration and plot it on the y-axis, such that the x-axis is time as the experiment proceeds and time extends. Well, we can see that if these values are x and y as shown, well, then the slope is going to be directly equal to negative k. See how the slope is negative? We have a negative slope because the concentration of A is going down. But the rate of a reaction is not negative. specific rate constants are positive. So negative k equals m. So if I have a negative m, that gives me a positive k, because I take the negative of the m that's negative, which gives me a positive k value. I can also see that b, or my y-intercept, is the initial concentration. So this is really valuable because we can read a whole lot of information. We can predict a lot of information as time goes by. Now for zero order reaction, we also plotted the concentration of A according to time t. For a first order, we saw that it was curvy. It was an exponential decay. This one's straight. So we've already plotted concentration of A according to time t. But we could also, for interest, plot the rate of the reaction for this zero order reaction against various initial concentrations of A. So if I did an experiment with a certain concentration of A that was really low, I could measure the rate. And if I doubled it, I could see that the rate stays the same. And triple it, the rate stayed the same. So the rate doesn't change if we mess with the concentration of A. Some enzyme kinetics occur according to zero order or pseudo-zero order. You can add more and more reactant to your reaction, but if the enzyme is saturated, well, you can add as much reactant as you want. The reaction isn't going to go any faster because the enzyme's already going as fast as it can. So a lot of enzyme kinetics are zero order reactions, or pseudo-zero order, once that enzyme gets saturated. So this is zero order. Then we have second order, and this is the final of our 3 integrated rate laws that we're going to discuss in our course. We know how to figure out if a reaction is second order. We simply compare experiments that were done at the same temperature, all the same conditions, except for those initial concentrations. And we can see how, when the concentration of a certain reactant changes, what happens to the rate of the reaction. And sometimes we see that the rate quadruples when we double the concentration of A. It's related by that change to the power 2. And we can identify that as a second order reaction. Well, if we have a second order reaction, we can't use zero order integrated rate law. And we can't use the first order integrated rate law. We need to use the second order integrated rate law. So we can integrate this Ka squared and the change in A over the change in time. I'll let you do the calculus on your own for fun. We get this, 1 over the concentration of A at time t minus 1 over the concentration of A at the beginning of the experiment, and that is equal to Kt. I'm going to move this piece, that initial concentration, over to the other side, and here is my second order integrated rate law. I'm lining it up, again, we've seen this pattern already, to y equals mx plus b. And when I do that, I can see 1 over the concentration of A at a given time is y. So I can plot this data, the concentrations that I'm going to do my experiments on, or as the concentration changes with time. But I'm not just going to plot it concentration of A according to t, because that gives me a curved line again, and those are harder to calculate. I'm going to plot it according to 1 over A, and when I do that, I get a straight line. If I get a straight line when I do that, I know that this reaction's occurring according to second order kinetics. Now it looks a little weird. We have a positive slope here as the reaction proceeds. Let's just say x is time t again. That's kind of old news. As the reaction proceeds, A should be decreasing, right? Because we're using up our reactant. So why do we have a positive slope? Well, A is still decreasing, but we should note that 1 over a small concentration gives me a bigger number by fraction rules. 1 over a big concentration gives me a small number. So it's still going from big to small. It just looks a little bit funny because it's in the denominator. when I do this, I can see as well 1 over my initial concentration is my y-intercept. This is the starting concentration of the reaction. And then I finally get a really nice, simple, direct correlation. The slope of the line is my specific rate constant, K. So if I do an experiment and I plot my data and I want to determine the specific rate constant, I don't have to work very hard. I simply look at the computer program that plotted my data and read the slope. Or I take 2 data points and I find the slope mathematically, and I see that the slope is equal to my specific rate constant. Nice and simple. Well, what if we plotted simply the concentration of A according to time t? If we didn't plot 1 over A, which gives us our nice straight line, we would see that the concentration of A decreases very quickly and then kind of slower as the reaction proceeds. Let's take a look at this sketch that we just drew. The concentration of A versus T for a second order reaction changes really quickly at the beginning. Here is my initial, there is about half. So the half-life for a second order reaction that we've drawn here is about this big. Maybe it's 3 seconds, 10 minutes, I don't know, something really small. Then if I half that again, maybe that's about half. Well, there's the second half-life. That's how long it took me to half that reactant concentration. And where's about half? I don't know, about there? Where's half? I don't know, it's off the screen. See how the half-life time changes as the reaction proceeds. So the time of a half-life for a second order reaction, or for a 0 order for that matter, isn't really as meaningful as for a first order reaction. First order reaction rates, that half-life time stays consistent, and we can do all sorts of interesting things with it. For 0 order and second order, it changes. So we don't talk about it quite as often. You still have the formula in your workbook, but you can see that it changes depending on what that new starting concentration is. And then we could plot the rate of the reaction according to the initial concentration of A. So if I did an experiment, let's say there, that's the concentration I had, I could measure the rate. If I doubled A, I would quadruple the rate. If I did it like this, we would see that it changes very, very quickly. Once we know these relationships, we can identify which equations to use and how to analyze a particular problem. All of these features are diagnostic for 0 or first or second order. So we need to be able to know how to interpret this important data. So let's go ahead and solve some problems with these new equations. Let's consider a reaction where the reactant, let's say it's AB, goes to products, and this data is plotted in a graph. And the concentration of AB to the power -1, we can write that out to the power -1, or simply write it out as a fraction. Mathematically, it's the same thing. And versus time. This results in a straight line. And I'm going to stop right there. Just with that information, if you didn't have the title on this question telling you what it was, you would be able to conclude that it's a second order reaction. And you would know to go to your formula sheet and pull out the second order rate law and use that to analyze this problem, simply because 1 over A, according to time, gives a straight line. 0 in first order, don't do that. So, second order kinetics here. And we're told what the slope is. What is the initial rate in moles per liter per second of this reaction when the starting concentration is 0.75 moles per liter? Well, I'm going to pull out my second order integrated rate law and see what I know and see if I can draw any conclusions here. I want to figure out the rate at a given moment in time. And I know that this is a second order law, so the concentration of AB will be squared. I want to figure out the rate at a given concentration of AB, of my reactant, at 0.85 or 0.75 moles per liter. Well, I want to solve for rate. I know the concentration of AB, but I don't know the specific rate constant K. So I go back to my problem and I say, well, did they give me K? Well, I don't see K written down. I don't see specific rate constant written down. But I am given a hint here that the slope equals 0.165 moles per liter. And I hate memorizing things, so I pull out this second order rate law and say, is there anything I can glean from this information? This rate law aligns with the equation for a straight line. I can see that m, the slope, lines up with k when I arrange it like this, y equals mx plus b. So that means that k equals m. I need to know my specific rate constant, and I do, because I was given the slope of this line when 1 over the concentration is plotted against time. So I simply need to know how to interpret this value. The slope equals the k equals 0.165 moles per liter per second. I know everything now. I can simply solve for rate. So let's do that. And you may notice that I corrected my units. Out of habit, I put moles per liter, but that is not the unit given to us for this specific rate constant. It's the inverse of moles per liter. It's liter per mole. And now I can see how liter and one of the liters factors out. One of the moles and the per mole factor out. I keep per second, and I keep one of these as mole per liter. This is why we get some weird units in the specific rate constant K, because we're multiplying it by concentrations to various powers, and all these units will factor out. So given this information, we can predict the rate at the initial point of this reaction will be 0.0928 moles per liter per second. So this is a hypothetical example. Let's go to a real example that's pretty interesting here. This reaction here, we have ammonium cyanate shown here, and it can produce urea, which is a fertilizer and something that we also pee. Urea was known to be a biologically sourced molecule. Ammonium cyanate, on the other hand, is an inorganic molecule. Back in 1828, a scientist named Wöhler was investigating this reaction. This was back when scientists were exploring inorganic compounds, but anything that was biologically sourced was considered to have a vital life source. So you couldn't make any organic molecules, or what we identify as organic molecules today, because those had to be made by people or animals, and they had life inside of these samples. They were vital sourced. Well, Wöhler showed that you could make something living, not quite living, but biologically sourced, out of something inorganic. And this was the birthplace of organic chemistry. Prior to this point, there was no expectation to be able to manipulate or synthesize any biological molecules. They were thought to have a living quality to them. Now we can see that they're simply atoms connected by covalent bonds, and we can synthesize these. If you ingest vitamin C, ascorbic acid, you could source it from an orange, or you could source it from a pharmaceutical company that synthesized that weak acid, and it's going to be exactly the same thing that goes into your body. It doesn't have to come from a biological source. That said, eating the orange gives you lots more nutrients, gives you fiber. Eat the orange over the pill. But it's the same molecule on the inside. So that's kind of cool about this reaction. So this rearrangement, we're told, is a second order reaction, and it takes 11.6 hours for the reactant concentration to go down from the starting amount to 0.0841 moles per liter. So we have to solve, well, what is the specific rate constant for this reaction? It's a second order reaction, so I pull out my second order integrated rate law. We're told the starting concentration and the concentration at the time that we want to solve for, and we're told that it takes 11.6 hours to get there. The only unknown is the specific rate constant K, and that's what we need to solve for. So we can plug in what we know and solve for K. Okay, so we recognized what we needed to do. We plug in the numbers. We get our specific rate constant K. That's great. Now we can solve something new with that. Part B, how fast would this new concentration of solution react? How fast would it be if we started with 0.839 moles per liter? That's not what we did in this original experiment. We started with like 1/4 of a mole per liter. Now we're going to start with more, but we can predict what would happen because we know K. So I'm going to say, well, the rate is equal to the specific rate constant of my reactant squared because it's a second order reaction. I want to know how fast is it going. I've solved for the specific rate constant K, and I know the starting concentration of my inorganic compound that's going to give me something organic. Okay, so there we go. The rate at this higher concentration would almost be 0.5 moles per liter per hour. So, question for you. Now that we've done a lot of analysis of these types of problems, classify these reactions. Chat with the person beside you for 1 minute or 30 seconds. And 5, 4, 3, 2, and 1. Okay, we have second and first. Indeed, this is correct. If we didn't remember, we could look up in our workbook and then also see that the summary chart in our workbook is here, and that this summary chart is in our formula sheet for our exam. And I can simply see how the concentration of A is provided in these various formats, in these integrated rate laws. Reaction 2, this is just remembering that isotopic decay occurs according to first order kinetics. A way to remember is that we talk about radioisotopic decay in terms of half-lives. I'm going to change my batteries for 1 second here. Okay, we are back. I wanted to draw your attention to the fact that we have some learning objectives throughout your workbook. So if you're looking for a study tip for our upcoming exam, check to see what the objectives are at the beginning of every topic. And how confident are you in doing all of these things? For example, by the end of this topic, you should be able to explain rate law, specific rate constant, integrated rate laws for all these 0, second, and first, exponential decay, and half-life. If you can confidently explain those to your roommate, you're good with point number 1. I'll jump to the last point. Use data to find reaction rates, half-lives, final concentrations for 0, first, and second. This gives you a good idea of what to expect on an exam. These are the key concepts that we want you to walk away with. So odds are you may see some of these coming up. Okay, let's jump into topic 5.2. So our very final topic of this course. I'm going to let you turn the page for like 10 more seconds, and then we'll get started. And 3, 2, 1. Okay, we're going to get started again now that everyone has turned their pages. Question, do we get these integrated rate laws on the exam? Yes. So the formula and data sheet that will be provided to you and stapled to your exam booklet was posted online in January. So if you go to reference information on OWL, you can find the PDF of this formula and data sheet so you know what you're going to be given on this exam. Okay, we've been chatting about how to figure out the order of the rate law. Now we're going to come to the conversation of how we can use rate laws to determine reaction mechanisms. As well, we're going to see how we can analyze rate laws and see how temperature and catalysts can affect the rate of a reaction. In topic 5.1, we really just looked at concentration changes. But now we want to look at these other factors like temperature and catalysts and drawing conclusions about reaction mechanisms. This takes us to a reaction coordinate diagram. Let's start with this picture here. If this ball needs to get from point A to point B, it has to get over this bump in the road first. We can see that at point B, it's going to be more stable. It will have lower energy, a lot more chill. But in order to get to this more stable, lower energy position, it has to get over this bump. It has to get over this activation energy. Let's imagine that this is you in your nice, cozy, warm bed this morning. Now you know that you're going to have a great day. You know that you get to come to chemistry class, you're going to have dinner with some friends. You have an awesome day ahead. This is favorable for you to get up and have a fabulous day. You know it's going to be amazing. You know it's going to be amazing. Spontaneous, Gibbs free energy is in your favor. But you have to get over this activation energy. Right now you're warm and cozy, and you have to like get out of your covers and like put your feet on the cold floor, and the house is still cold because maybe your furnace didn't kick in yet, and you haven't had breakfast yet, and you have to put in a lot of extra energy to get to this more awesome place like your chemistry class, okay? We know we want to get there. Thermodynamically, this is favorable. But kinetically, it might not happen unless you can get over this barrier, this activation energy barrier. The size of this barrier is distinct from our final position. The barrier tells us how fast this is going to happen. This activation energy tells us the kinetics of the reaction, how fast or slow it will happen. And it has nothing to do with the fact that we're going to be happy and cozy over there. So you have to get out of bed, but then you know you're on your way for the day. Well, we could consider a catalyst. Let's imagine you're cold in your bed, and it's really awful to get up. You don't want to have to get out of your covers. But then someone comes and they bring you a nice warm house coat, and they hand you a cup of coffee, and you're like, okay, this isn't so bad, and they could lower that activation energy, okay? That's what catalysts do. They lower that activation energy. But we need to know how to interpret these diagrams. Let's look at this example with the combustion of methane. We know that this reaction is exothermic. It gives off heat. We also know that, because we've talked about it so much, that it is thermodynamically favorable. Gibbs free energy tells us that this is, well, enthalpy tells us it's exothermic. Delta G tells us that it's exergonic, but it's favorable. It's spontaneous. But if I have a little gas sample of methane, I could hold that for a moment, and it doesn't spontaneously burn in my hand. I have to do something to make it light. I have to add a little spark with my barbecue lighter, for example, or a little spark in my stove to give it that little kick to get over the activation energy barrier. And then this exothermic reaction can keep that heat going and allow the other methane molecules to combust. But I do need to do something. I need to give it a little kick in the butt, a little spark to get it going and over this activation energy. Here are my reactants plotted on this reaction coordinate diagram. Energy is on the y-axis. I can see that my products, carbon dioxide and water, are lower in energy. They are more stable. I can see that the delta H for this reaction is negative. It's exothermic, it's going to give off heat, but I still need to have that little spark to get it going. We need that spark to get over this activation energy barrier. Now, I've talked about the y-axis. This x-axis is called the reaction coordinate. It's not exactly time, but you can kind of think of it as like storyboarding in a cartoon. This happens, and then this happens, and then this happens. It's how the reaction progresses and as a measurement of energy. So I'd like you to think about, well, what's happening at the atomic level for a reaction to occur? I like to think of reactions in this way here. Let's see if I can get my video. Give me 1 second to pull this up here. There we go. So molecules need to collide for a reaction to occur. They have to collide with sufficient energy to overcome this activation energy barrier, and they have to collide in the correct orientation to ensure the reaction can proceed. So this is what I imagine when I think of molecules colliding. Has anyone ever done bubble soccer before? Okay.
Can I get down like this?
Okay, so that's what we can imagine is happening when molecules collide, okay? So they have to smash into one another with sufficient energy to overcome that activation energy barrier. Well, molecules at a low temperature, we can plot their kinetic energy as a distribution. If we had, say, 1,000 molecules or 1,000,000 molecules, and we plotted their kinetic energy, some are moving faster, some are moving slower, some have more energy, some have less energy. It's a distribution, just like we talked about gas speeds being a distribution. At a low temperature, the kinetic energy is lower. But if we change the temperature, if we increase the temperature, the distribution widens, and we end up with more molecules having higher kinetic energy, higher levels of energy. The activation energy for a given reaction is going to be different for any reaction, but there is going to be an activation energy for any reaction. For this example, let's consider if I had methane at a really low temperature and I didn't give it a spark, not enough molecules would meet the activation energy. But if I heated up that methane or I added a little spark, I would change this distribution. By increasing the temperature, more molecules have more energy to overcome that activation energy barrier. So we can get these molecules to have sufficient energy to overcome this activation energy barrier and to get on with their wonderful life. But when it's at the very top here, we have a transition state. Perhaps if it's two molecules, they have collided. It has enough energy, but it could go back and make the reactants again, or it could fall over and proceed with the reaction. Just because you have the activation energy doesn't mean that every reaction is going to successfully happen. It depends on some probability factors and the probability that it can continue to the products. So some molecules, some transition complexes will just go back to what they were. Some move forward and get on with the reaction. Well, when we introduced the idea of the rate law, we had this specific rate constant K. And hopefully I mentioned it's a nice little gift-wrapped package, and it has a lot of information in it. This specific rate constant K includes this activation energy, the height of that bump that we have to get over. It includes the temperature. Changing the temperature changes the rate of a reaction. It includes the gas constant, just 8.314, but now we're going to measure it in joules per mole Kelvin. And it has this A factor for Arrhenius. It's a probability factor. It's sort of a measure of how easy it is to get to the reaction site. It's a probability factor, and it's unique for a given reaction. The rate of a reaction is going to depend on the number of collisions. If you only have one collision, well, the rate's not going to be very fast. But if you have 10 million collisions, well, there are just so many more chances for that reaction to happen successfully. There's the probability factor, that steric factor A, how easy is it to access the site, and so on. And then, how many of these collisions have enough energy to overcome that activation energy? So what's the temperature, and how does that compare to this activation energy? This specific rate constant K has this E function, and I've plotted it here. I'd like you to go ahead and interpret this Arrhenius equation, defining for us what this specific rate constant K is. How does activation energy, the magnitude of its big or small, impact the specific rate constant K, and in turn, the rate of the reaction? Chat with the person beside you for 1 minute. Okay, and 10 more seconds. And 3, 2, and 1. Okay, approaching D, and D is the correct answer. We could think about this in this way, qualitatively. If I had the same delta G, or the same delta H, the same change in energy of reactants and products, I could have a big activation energy, a huge hill to get over, or I could have a little activation energy. The little activation energy, that reaction can proceed a lot faster. But that big activation energy is going to result in a smaller reaction rate, which means a smaller specific rate constant. You can also think about the function of e to the negative x. This is e to the negative EA. As EA gets bigger, it's even more of a negative exponent. That makes K smaller. Or if you want to think about the e to the power x that goes this way, it gets more negative and goes this direction. So you can think about it from the formula, you can think about it from the diagram. Either way, we end up with a slower reaction rate when we have a big activation energy to overcome. So let's analyze these reaction coordinate diagrams. How fast a reaction occurs, the kinetics of a reaction, is distinct from the thermochemistry of that reaction. How fast the reaction goes doesn't really have much to do with the overall change in energy from the reactants to the products. Let's look at these 4 examples to illustrate that point. Part A, rank these reaction coordinate diagrams in increasing rate constant, or according to increasing rate constant. Increasing means from small to big. Well, a big specific rate constant means a small activation energy, and a low specific rate constant means a large activation energy. So I'm going to write down what I actually want to compare them to. I want to write from a large activation energy to a small activation energy. So let's start with line A, right here, reaction coordinate A. From this experiment, we can see the reactants start here, the products end at the A. We measure the activation energy by drawing across the energy level of the reactants and then going straight up at the tallest point. This is the activation energy for A. Well, we could do this for B next. Here's the starting energy level for B. The activation energy for B is right here. For C, it gets a little tricky to see them apart. Here's the activation energy for C. And then for D, the biggest dashed line, we go across and we can draw out that activation line for D. So I have A, B, C, and D, and I need to order them from largest activation energy to smallest activation energy. The longest line belongs to reaction A. It's the biggest overall activation energy, the biggest climb in energy. The next tallest, go ahead and shout it out. What's the next tallest? D. What's next? And there we go. Let's change it up now and look at this in terms of the thermodynamic favorability. Low thermodynamic favorability would be reactions that are endothermic, reactions that require energy going in, where the products have more energy than the reactants. We have to put in energy to make it happen. In contrast, more favorable reactions tend to be the exothermic reactions, where energy is given off. If energy is given off, that means the products have lower energy or are more stable than the reactants. So now we don't actually care at all about the activation energy. The thermodynamics has nothing to do with the activation energy. Now I simply want to pay attention to the starting point and the ending point. So let's look at A, the start of A and the end of A. The difference here is that big line for A. All this energy needs to be put in to make reaction A happen. Well, let's look at B. Here's the start of B, the end of B. It's kind of hard to tell if it goes up or down. Let's just call it a little itty bitty up. For C, I can see this dashed line starts here and ends here. Initial to final, C decreases. That would be exothermic. And then D, the longest dashed line, goes from about here down to there. So we have to figure out, well, which one is the least thermodynamically favorable? Which one is most endothermic? Go ahead and shout it out. A, that's right. Which is next most thermodynamically favorable? And, well done. ABCD is different than ADCB. The order is different. They have different kinetics and different thermodynamics. So we need to know how to read these different pieces of information from these reaction coordinate diagrams. Have a fabulous weekend. I will see you on Monday.